So, hello everyone, and welcome in. My name is Brian. I'm the Department Chair of Mathematics at Okanagan College, and today we're going to be looking at the Euler Phi function. Now, the first question we might want to ask is, what in the world is that, and what is the whole point of this thing? So, the Euler Phi function basically counts for us. And what we're going to be after is the number of integers less than n. And specifically, we're just looking at positive integers here. The number of positive integers less than n that are co-prime with that particular number. So that's effectively what the Euler Phi function is going to do. I'm going to go ahead and just set up a proper definition for you guys. And then we'll take a look at some examples. And for the Euler Phi function, we're going to call it phi or phi of n. That's going to be how it's denoted. And like we said, we want the number of integers less than n that are co-prime with n. Are there any prerequisites for this? For this talk, I don't think so. You'll just need to know some basic rules of prime numbers. I think that's basically it. So it should be a really nice, I'm hoping it'll be a really nice introduction to the theory of the Euler Phi function. So let's list the first couple of numbers and try to determine the corresponding number of co-prime integers. So we should be able to do, according to the definition, we should be able to do this for any positive integer. So we could start at 1. Maybe we'll just list the first 10. Let's say 3, 4, 5, and we'll go all the way up to 10. We'll add some more rows here at the end. So we don't really have any positive integers that are less than 1. So typically what we do for the case where n is equal to 1 is we just make a definition that the Euler Phi function is defined to be 1 for this particular value. So this is a special case. It's kind of like 0 factorial, where it doesn't really fall into the pattern that we're trying to create. So we just define it in a particular way to make the overall theory make some sense. So in this case, we'll just define phi or phi of 1 to be equivalent to 1. That'll be our definition. Now, for the number 2, there's only one positive integer less than 2, and 1 is co-prime with 2. So phi of 2 is also equal to 1. And if you want, you can kind of keep track of the numbers over on the side that are co-prime with that given value of n. So for example, for 3, both 1 and 2 would be co-prime with 3. So we expect phi of 3 to be equal to 2. Now 4 is probably the first interesting case. If we look at all the numbers less than 4, we have 1, 2, and 3, but 2 is not co-prime with 4. because they both share a factor of 2. So it's only 1 and 3 that happen to be coprime with 4. So we have that phi of 4 is equal to 2 as well. Now for 5, 1, 2, 3, and 4 are all coprime with 5, so phi of 5 is equal to 4. What about 6? I'll do 7. 7's another fairly straightforward case. Everything is coprime with 7. There are no numbers less than 7 that share a factor with 7, so phi of 7 is 6. But what about 6? What should be my list here? And what should be my Euler Phi number associated with the value of 6? So let's see, 6 has factors of 2 and 3. So I can include 1, but I cannot include 2 or 3. I cannot include 4, because 4 also shares that factor of 2. But I can include 5. So it turns out that phi of 6 is equivalent to 2. There's only 2 numbers less than 6 that are coprime with it. Just 1 and 5. Okay, we've done 7. Moving on to 8. So 8 has only factors of 2, right? It's 2 times 2 times 2. So as long as we don't have an even number, we should be okay. So 1, 3, 5, and 7 should all be coprime with the number 8. So phi of 8 should be 4. And let's finish up our last two. 9 is a perfect square. It's 3 times 3, so 1, 2. We cannot include 3, but we can include 4, 5. We cannot include 6, but 7 and 8 should be okay. So that gives us 6. And then for 10, we cannot include any even numbers, nor can we include any multiples of 5. So 1, 3, 4, 5, 6, 7, 8 we cannot include, but 9 we should be able to include, so we should get 4 here. Okay, so that gives you an idea of, just working through the first couple of integers, what those Euler Phi functions return. So inputting a value n, I'm looking for the number of coprime integers less than n. So that's what we're looking for. Now, there are a couple patterns that I think are interesting right away. Like if I look at, for example, 5 or 7, or maybe even 3 is a good one too, right? Here are all of my prime numbers less than 10. 2, 3, 5, and 7. So I think right away, we can probably convince ourselves that finding the Euler Phi number for a prime is relatively straightforward. Every number less than that prime number is coprime with it because prime numbers don't have any other factors other than 1 in itself. So that leads us to our first theorem, which is the following. If I'm given a prime number, then the Euler Phi of that prime number is always p minus 1. It's always 1 less than the prime number that we're working with. And that's because there's always a collection of p minus 1 numbers that are going to be coprime with that particular prime number. So I don't really think we need to prove that one. I think that one's like fairly obvious. All of those numbers are going to be coprime with that prime number. Okay, so if I take any number less than p that's a positive integer, and I try to find the GCD of the prime number and that number that's less than p, I always get 1. So when there's p minus 1 occurrences of those values. So let's see. I kind of want to lead through a couple examples here. So the next interesting case that I want to look at is what happens if I have a prime number and I raise it to some kind of power. So here p is prime. So this could be a number like 9 or 25 or 81, numbers that are just strictly powers of prime numbers. So we had a couple examples. I think was it just one example? Just 9. A 4, I guess, falls into this category too. So 4 is another example of this. So let's grab 4, 9, 25 as like some squares. Right, so if, let's say this is, so if pk was equal to 4, this is 2 squared, the co-primes, and then we'll also list phi of n as well over here. So phi of n I think was 2 in this case. Our co-prime numbers were 1 and 3, right? 1 and 3. If we had, I'm just going to maybe write this chart a little bit nicer. So this is pk, this is 4 equal to 2 squared. We also had another example, which is 9, which is 3 squared. Our co-primes were 1, 2, not 3, 4, 5, not 6, 7, and 8. So in this case, we had 1, 2, 3, 4, 5, 6 co-prime numbers with 9. Now, I'm going to do one more squared example, and then maybe we'll try to look at a larger example where we have something that's bigger than squared, so you can kind of see the patterning that's happening here. Let's take 25, which is 5 squared. And all I'm going to do in green is just list out all of the values less than 25. So these are all the candidates that I can draw from. To create this set of coprimes with 25. Sorry, I don't want to include 25 on that list. So the next thing I want to do is start thinking about what numbers are not going to be coprime with 25. Well, the only prime factor of 25 is 5. So any multiple of 5 we have to rule out. So 5 is gone, 10 is gone, 15 is gone, and 20 is gone. The remaining values here should be what we take for the set of coprime numbers. So what did we remove here? We removed 1, 2, 3, we removed 4 numbers. And that's going to leave us with 20 numbers, right? So we started with 24 numbers altogether. We removed 4 of them. So we get that phi of 25 should be 20. And that's kind of the procedure that we want to use here. So if we kind of think about 4, we'd be able to draw from these 3 candidates, but we're going to remove the multiples of 2, right? Which is this. If I'm thinking about 9, my candidates were 1, 2, 3, 4, 5, 6, 7, 8, 9, 7 and 8, sorry. And then I'm removing the multiples of 3 to do this. So that's kind of the general strategy that we use here. We're basically going to say, okay, well, let's look at our full list, which is p minus 1 numbers, and then we start removing the multiples of p until we get to the highest number on this list. So that's how the proof generally works here. So I'm going to just write down the theorem here. Well, we should be able to have enough firepower, hopefully through those examples, to be able to prove the theorem. And it goes something like this. So let's say we have p as a prime number. Then, if I want to find the Euler Phi, and I know that the number that I'm inputting into this function is p to the power of k, then what I get is this. I get p to the k times 1 minus 1 over p. So this is the formula. So let's go ahead and try to prove why this formula works. Now notice it looks a little bit weird, but what happens if we distribute this? If we distribute p to the k through the brackets, what do we get? We get p to the k minus p to the k over p. Or in other words, we get p to the k minus p to the k minus 1. So that gives me some insight into how we're thinking about creating this Euler Phi number. We're starting with p to the k, which is like all of the positive integers up to that number we're working with. And then we're subtracting off p to the k minus 1. So in other words, if we come back up to this example where we looked at 25, I'm just going to maybe draw a line here. So when we were looking at 25, what this theorem is saying is, well, why don't we just start with all of the numbers from 1 to 25, and then we're going to kind of systematically go through these numbers and remove any multiple of 5. And so our goal now is to convince ourselves that there's exactly p to the k minus 1 multiples that we need to remove from this list. So that's the idea. Hopefully that makes sense. So same thing here with 9. Maybe look at a smaller example. If we go all the way up to 9, which is 3 squared, we need to remove then 3 multiples of 3 on the way up to 9. So there's, 3 to the power of 1 multiples that we remove. Down here, there's 1, 2, 3, 4, 5 multiples of 5. So we remove 5 to the 1 multiples from our list. So that's the idea. Okay, so we can maybe just do a quick little proof of why this works here. So we saw that the idea here is to subtract all multiples of p between 1 and p to the k inclusive. We do have to subtract that p to the k term because we don't want to consider that term anyway. So the idea is we need to remove the following. So we need to remove the prime number itself, 2 times that prime number, 3 times that prime number, and we just keep going until we get up to here. So p to the k minus 1 times p. Remember that this number here is actually p to the k, right? So we need to remove all of these multiples. How many multiples are there? There's actually p to the k minus 1 multiples that we need to subtract. So that's the other kind of key thing here. How many of these are there? There are p to the k minus 1 multiples we need to remove. Okay, so therefore we start with p to the k. That's our full list. We're going to subtract off the multiples that we don't want to consider, and that leads us to the formula that was given in the statement of the theorem. So we just factor out p to the k here, and we get 1 minus 1 over p. All right, so now we have some kind of basic strategies for working with simplistic numbers. We eventually want to extend this strategy to be working with a bunch of other numbers too. But for now, we should be able to do some basic evaluations with prime numbers or powers of prime numbers. So let's say we had to calculate these two values here. Phi of 17 So how many numbers are co-prime with 17? And phi of 64, how many numbers are co-prime with 64? I'm going to go ahead, actually I'll pull out a calculator on my laptop. Because for sometimes with these large numbers, it's sometimes helpful to have a calculator. So we'll get that fired up in case we need it. For 17, we note that 17 is prime. So we have an easy way to think about phi of a prime number. It's going to be all of the numbers less than that number. They're going to all be co-prime with 17. So there's 16 of those numbers that are co-prime with 17. For 64, we want to think about this a little bit differently. We want to think, okay, 64 is what? 2 to the power of 6, I think, right? 2 to the 6. I think that sounds right. So we now have a formula to deal with this. This is going to be 2 to the 6, right? P to the k times 1 minus 1 over p, right? In our case, the prime number is 2. Or another way of writing this is it's going to be 2 to the 6 minus 2 to the 5. Okay, so we have 64 numbers that we start with all together. 32 of those are going to be multiples of 2 as we go from 1 all the way up to 64. So we're going to be left over with 32 numbers. And that kind of makes sense, right? Like if 62 only has its only prime factor is 2, that means all of the odd numbers should be co-prime with 64, is basically what we're saying. So that kind of intuitively makes sense to me. Okay, so that's how we kind of deal with prime numbers and powers of prime numbers, but we do want to eventually work with other kinds of numbers too, right? Like, even in this list from 1 to 10, we have numbers like 6 or 10, or I guess 8 has been taken care of, right? So we've taken care of 4, that's a multiple of 2, or sorry, a power of 2, 8 is a power of 2, 9 is a power of 3, but we're still left over with these other numbers that could be composite kinds of numbers, right? So like 6 is 2 times 3. It has a factor of 2 and a factor of 3. 10 is 2 times 5, right? A factor of 2 and a factor of 5. So I do want to eventually extend out and be able to do this for more generalized numbers. So that's where we want to go next. So how do we extend this out to deal with other kinds of composite numbers? So let me just have a quick little peek here. So the next lemma is as follows. And I want to, again, probably explore this a little bit through some examples before we go ahead and try to prove this so that we get an idea of where this proof comes from. So let's say P is prime. And let's assume that this prime number divides n. Okay, so n is a larger value here, maybe a larger integer. Then the lemma says that if I have a prime number times n, right? So the number inside here that I'm inputting into the Euler Phi function is p times n. Then I can factor out p and just consider phi of n. So that's kind of interesting. That's an interesting lemma. So can we put ourselves into a situation where we can explore this? Let's look at maybe an illustrative example.
Obviously, you mean omega n distinct prime factors. Omega k also 1. And if you want a prime power indicator, use 1 if n pk, or von Mangold. Lambda gives log p. Zeta, simple. So, say hello, yeah.
Yeah, I assume, Jeff, that the couple lemmas that we're going to take a look at are the building blocks that we need to prove the generalized theorem. That's kind of what my intuition says here. Yeah, so we have arguments for primes, we have arguments for prime to the k, and Smeagol, you're right. We want to kind of build and try to develop a formula that's going to work for any composite number, which is a little trickier to do. But it's all going to hopefully boil down to like how we count things and thinking about how we count things appropriately. So the example I have is the following. Let's consider phi of 36. So phi of 36. And we can note that phi of 36 is equivalent to phi of 3 times 12. So we have the conditions in the lemma that we need. We have a prime number that divides n, and right, so 3 divides 12, and we have phi acting on this overall number, which is 36. Right, so that's, I guess, the first thing we need to know here. So here p is 3, n is equal to 12. That's a terrible arrow. So what I'm going to do is I'm just going to list the numbers from 1 to 36, because those are going to be the candidates that we kind of care about. And I just want to make sure that I'm listing this in the right way. Okay, so I think I see what I want to do here. So here's our list from 1 to 36. We know that any multiple of 3 we have to remove. So let's go through and just remove our multiples of 3. So 15, 18, 21, 24, 27, 30, 33, 36. So that's removed our multiples of 3. We also have a factor of 4 inside of the number 12, right? So any multiple of 4 also has to be removed from this list. So maybe I'll just use a different color. I'll use red to kind of show the removal of these other values. So 4, 8, 12 would be the overlap. 16, 20, 24, 28, 32, and 36. Holy fuck, stop texting me. Will the stream be on YouTube? Yeah, once I edit it, it will be posted up to YouTube. What else am I missing? I'm missing. Oh, it's not just 4. Sorry, it's also there's a factor of 2 in here. I'm not really. It's a factor of 2, not a factor of 4. So I should actually be removing the even values here. So 2s, 4s, so these would also get removed. There, and then these here. So my fault there. So it should be a factor, the multiples of 3 because of the factor of 3. And then 12 is 3 times 4. 4 is really composed of factors of 2. So I want to remove all the even values here as well. And so what we get as a result are a list of numbers that looks something like this. So here's the leftovers. I get 1, 5, 7, 11, 13, And I'm being very kind of careful about how I align these things because there's an interesting property I want you to see. And then 25, 29, 31, and 35. And we're going to do something just a little bit funky, and we're going to think about the collection of numbers that are co-prime with 12 as well, and just kind of compare that to the list that we have. So this list that we have over here, like this big list, is my candidates for this, right? So I kind of expect there to be, 4 times, right? I expect there to be 12 candidates for phi of 36. Now for 12, I have 1, should be fine, 2 is not fine, 3 is not fine, 4 is not fine, 5 is fine, 6 is not fine, 7 is okay, 8, 9, 10 are not okay, and 11 is okay. So here are my candidates for phi of 12. And what I notice is that these candidates are exactly the first 4 candidates for phi of 36. And what we're getting, in some sense, is if I look at like the next group of candidates, so I kind of go down and I look at these 4 candidates down here, these 4 candidates have the same remainder after doing division by 12, right? So 13 divided by 12 would give me 1, or 13 mod 12 is 1, 17 mod 12 is 5, 19 mod 12 is 7, and 23 mod 12 is 11. And it's similar for this other group here as well. So arranging these things in kind of strings of 12 kind of gives us some insight into how this proof is going to work. So basically we're going to be arguing that we're going to be looking at this smaller mod, which is 1, 5, 7, and 11. Those are this smaller collection of numbers, which is phi of 12. And we're basically looking at remainders after division, right? So anything that has remainder 1, 5, 7, or 11 mod 12 are going to be the candidates that we need as we move our way up to 36. So it's really, really, really interesting, the setup for this. But that's kind of the basic idea. So let's go ahead and try to prove this, at least try to convince ourselves of the method of attack for these kinds of problems. So proof. Have to work on your circuits class. Well, have fun with your circuits class, Smeagol, and thanks for coming and joining. Okay, so the first thing we're going to do is note that all numbers that are relatively prime to our starting number are also going to be relatively prime to n. Okay, so what does that mean? With our illustrative example, we're saying, okay, all of the numbers that are relatively prime to 36 should also be similar to the numbers that are relatively prime to 12, right? Like, basically, I can look at this smaller list and extend it out to a larger list that's going to work for 36. Okay, and that's because p divides n, so we've already removed the multiples that we need to. And maybe I'll just write that in here. So this is because of our assumption that p divides n. So when we scale n up to p times n, we're going to get p copies of the objects that we want to look at. Okay, so we're thinking about this formula in terms of, in a multiplicative sense. So if I ever have like p dividing n and I'm looking at p times n, since p divides n in this particular case, I can really just look at the smaller number, which is phi of n, figure out how many numbers are co-prime there, and then we're doing a multiplicative argument to kind of scale up to get this number that we want. So that's kind of the idea in this particular lemma. All right, so what might work here? I feel like 2 and 10, 2 and 10, 2 and 40? 2 and 40 might work. 5, well, we could do it a couple different ways. Let's try 2 and 40. So what if we broke this up and we said 2 times 40? All right, so I have a prime number that divides into n. So what this is saying is that we should then really be thinking about this as 2 times phi of 40. Do we have a way to deal with 40 yet? I don't think so. Right, 40 has 5s and 4s, 2s. So I don't think we have a way to deal with this quite yet. So that's probably not the way to go. At least right now. Okay, so that's not going to work. What if we write this as... How else can we do this? What if I take 5? Is that 20? So the idea here is we need to kind of pick something that would get us into a range where it's easy for us to kind of work, right? Like, I don't know how to work with 40 quite yet. That's a bit too big. But what if I take 80 and I divide by 5? That would be 16. 16 I know how to work with because that's just going to be 2 to the power of 4. So I think that should be okay. But in this case, 5 doesn't divide 16, does it? So that's not helpful either. What other prime numbers do we have? 3. 5, 7 doesn't work, 11. I guess maybe we have to try 2 and 40. Maybe 2 and 40 is the way to go. I'm trying not to look at my notes so I can kind of like guide you through my thought process on what we're able to do here. So this certainly could work. This would leave us with 2 times, according to the lemma, we would get something like this. Can we do the same thing for 40? So can I pull out another factor of 2 here? And go like 2 times 20? That seems like something I can do, right? So maybe rewrite this as 2 times 20, and then I can use the lemma again. So this would be 2 times phi of 20. And then we do 2 and 10. And then 10 is small enough that we can probably just list everything out. Even 20 is small enough we can probably list everything out too. But just maybe for the sake of kind of seeing the full argument, let's do it one more time. We can factor out that last 2. And we know what phi of 10 is. So this would be 2 times 2 times 2, which is 8. And the Euler Phi function for 10, we've already solved that up above. It is... Where is that one? It's 4. 1, 3, 7, and 9. Okay, sweet. That's exactly what I have in my notes. That's great. Okay. So this is kind of interesting too, because this now gives us a general strategy for pulling out primes. So in fact, up here when we started with 80, we could have just said, well, let's just rewrite this as p to the k times n, where I know p to the k divides n. So I could have rewritten this as like 8 times 10, right? And I know that each of those factors of 2 I can pull out. Okay, that's kind of interesting. So there must be a way to generalize that somehow, probably if they're co-prime. But anyway, that would be the thought process. Find a prime number that divides into that remainder, right, upon division, or that quotient. And then for us, it was just kind of keep repeating that process until I get to a number that I know, or a number that I know how to work with. Okay, so the next question is, we've dealt with the case where the prime number divides into n, but what if the prime number doesn't divide into n? Is there a way to think about that? So that's going to be our next lemma. So if p is prime, and p doesn't divide n, and here is that kind of larger integer number that we're working with as kind of like the factored form, then we have the following. Then if I start with p times n, and I know that p does not divide n, then I can simplify this as p minus 1 phi of n. Oh, that's interesting. Okay. So here we need p does not divide n, and p is prime. Why is that the case? So again, this looks kind of like a multiplication. So it feels very similar to what we were doing before, where we make p copies of phi n, but we have to remove phi of n things. Okay, I think I see probably how they're going to set this up. Can I pick a reasonable example? So let's take the one from above, right? Like if I have phi of 80, I don't really want to list 80 things though, so maybe I'll make this smaller, like phi of 20. And we think about this as, we'll grab a prime number that doesn't divide into the leftover stuff. So they're saying that this should come out to be 5 minus 1 times phi of 4, right? So in other words, I get 5 times phi of 4 minus phi of 4, and that should be 1 and 3. So it should be 5 times 2 minus 2, or 10 take away 2. So my goal is to try to figure out where these numbers are coming from. And usually I do that by kind of like, to get an intuition about how these things are working, I usually tend to write out these numbers. Now this n number is kind of important. In our last example, when we were looking at the values here, we kind of grouped things in groups of 12, right? Because that's this phi of 12 became part of how we think about this problem. So I think that's going to be similar down here. We're going to have phi of 4 is how we kind of think about this problem. So I'm going to arrange things in groups of 4 on my way up to 20. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So where are these groups coming from? So this is going to be all of the things that are... I'm basically just going to be looking at this first row and going, okay, what's co-prime with 4? That's going to be the 1 and the 3. And the 5 times 2 represents removal of all of these things, right? So everything that's left over should be 5 times 2. In other words, the 5 times 2 comes from looking at 1, 3, 5, 7, 9, 11, 13, 15, 17, and 19. Now, the formula says we need to subtract 2 more things, and these 2 more things, where are they? 5 and 15, right? So I have to get rid of 5, and I have to get rid of 15. And so why are 5 and 15 here, those two numbers are here because 5 does not divide 4. So I have to go back and I have to remove the multiples of 5 along the way. And so this formula is saying to remove the multiples of the prime number, there's actually going to be phi of n of those. So it's a little bit tricky to motivate this. But it's interesting that phi of n of those things are always in there. If we count all of them, maybe we'll get some insight if we count all of them. So all of the multiples of 5 would be here. So those are all of the multiples of 5 on the way from 1 to 20. And oh, that's interesting. So we expect to see 4 of them on the way up to 20 because we're in a multiplicative by 4 environment. And they're saying that a couple of these are already going to be crossed out, is basically what they're saying. So rather than subtracting 4, we're going to be subtracting phi of 4, so the ones that haven't already been crossed out. So that's kind of what this 2 means. So instead of subtracting all 4 multiples of 5, we're only subtracting the ones that haven't been removed yet, which is going to be represented by phi of n. Interesting. So I'll try to give like a rough idea of the proof here. It's very similar to what we talked about before. You kind of create your array, and then you're going to be looking at the multiples of that prime number up to p times n. And there's only going to be a certain number of those that are co-prime. Those are only going to be there's only going to be a certain number that we need to remove that haven't been removed already, and that's what phi of n is representing here. So I think that's kind of the rough idea. Okay, so what we did was similar to what we did before. So we kind of took this array and crossed out numbers that were co-prime with 4, right? To get our 5 times 2, or our p times phi of n. It doesn't represent the numbers, it represents the cardinality. So it's going to remove all of those values that are not co-prime with n. Right? All the way up to, in our case, up to 20. So it removed all of the numbers that were even. Now, doing this doesn't necessarily take into account the prime number like it did the last time. So if we compare it to what we did the last time, when I removed all of these values that were not co-prime with 12, because 3 divided into 12, I had already removed all of the multiples of this prime number 3. So I didn't have to do any extra work. All I need to do was this multiplication to get this array. Now down here, we do have to do a little bit of extra work, right? Because this prime number doesn't divide 4. It doesn't have any shared factors with 4. So I have to do a little bit of extra work in subtracting off those extra values. That are co-prime, right? That are co-prime with n. I think that's correct. And maybe I'll just be a bit more specific. We want this to be less than Pn. The next step is to take into account the multiples of P on the way up to Pn. And the formula is saying there's exactly phi of n of those. So what we do is we create our array, subtract off those remaining multiples of p that we need to get rid of, and we're left with the formula in question, which is p minus 1 times phi of n. All right, so let's take a look at another example. I'll show you the kind of array method one more time so you can kind of get a sense for how these numbers are being created. From your perspective, you just kind of need to know how to utilize, how to take a large number and break it down into primes that either divide the leftover portion or don't divide the leftover portion, and how to make that work. So let's consider phi of 30. So if I want to work with this number, I might say, okay, I can break this up into 3 times 10, just as an example, right? 3 times 10. Now, what I have is a prime number, p. So here's my prime number, p. Here's my n. And notice that p does not divide n. Okay, so 3 does not divide into 10. It has no shared factors whatsoever. So, if that's the case, our formula says we should be able to rewrite this as p minus 1 times phi of 10. So in other words, we should be able to think about this as 3 times phi of 10, which I think we know is 4, minus phi of 10. Okay, so I'm just going to write these numbers in and then simplify so we can kind of see how the array model works with this example too. So just going to double check. 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? So it should be 4. So we should get an array that's 3 times 4, and then we have to subtract 4 extras, so 12, take away 4. So our final answer should be, we should have 8 co-prime numbers with 30. So let's see if that is the case. Now we're going to be arranging these in rows of 10, because that's our n. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then let's start doing our cancellation of values that we know are not going to be co-prime. So let's start with 10. So we want to look for numbers that are even or have a multiple of 5. So we're going to get rid of all of our even values. And any values that are multiples of 5. So 5, 15, 25, 10, 20, and 30 have already been taken care of. Okay, so that should form this part of the solution, right? This should be now our three groups of 4, and I can kind of see that, right? So the leftover numbers look like this: 1, 3, 7, 9. Right, so there's our first group of 4, and then anything that shares modulo 10 with these values. So 17, 19, 21, 23, 27, and 29. So there's my array of 3 times 4. Now, the formula says I'm going to have to subtract off 4 more objects. What are the objects I'm going to have to subtract off? It's going to be, well, the multiples of this prime number. So 3, 9, and 21, and 27. So those are the 4 that I'm looking for that I need to remove from that array of 12 numbers. It's going to give me my final answer of 8. So 1, 7, 11, 13, 17, 19, 23, and 29. So that's kind of the formulation. That's how this part of that lemma works. It's saying, deal with the 10 and then come back, and it turns out that phi of 10 is exactly the number that I need to remove from the original number in order to get the updated number, right? So those are exactly the multiples of 10, or the multiples of 3 that haven't been crossed out already. So if we go back and look at the overall structure, here are our multiples of 3. 21, 24, 27, and 30. So there were only 4 other multiples of 3 we needed to remove on our way up. All right, so I think with those two lemmas, we can now prove the general case. So if we know that n has a particular prime power factorization, let's call it P1 with K1 as the power, then maybe I have a secondary prime with a different exponent, and this goes all the way to, I don't know, I call it PM and Km. Okay, so we know that we can take any positive integer, we can rewrite it as a factor of prime numbers. That is the fundamental theorem of arithmetic. So this theorem says, find that prime power factorization, then do the following. Then, if I want to know what the Euler Phi number is for n, we're going to go ahead and we're going to take n, and we're going to multiply by 1 minus 1 over those prime factors. So for each prime factor, we multiply by 1 minus 1 over that prime factor. Okay. Now, I'm just going to do a quick little read of the proof. I think we can prove this using the two lemmas. Oh yeah, okay. So we should be able to prove this without needing to see an illustrative example. So let's take a look at how to do this. So let's take phi of n, which we know is phi of p1 k1, p2 k2, up to pm km. Okay, so here's our prime power factorization. According to lemma 1, what did lemma 1 say? So lemma 1 said if we have phi of pn, this is equal to p phi n, provided that p divided n, right? So because of this, we should now be able to rewrite this original multiplication of powers of primes in the following way. We should be able to actually factor out most of our P1s. We can actually factor out K1 minus one of them. I can factor out all of them except for that last one. Same with P2. I can factor out all copies of P2 except for that last one. So all of these prime numbers can get factored out except for the last one. So I'm going to be kind of stuck with something that looks like this. Okay, so that's lemma 1. What does lemma 2 say? It says if I have Pn, it's equal to P minus 1 phi of n. This is if P does not divide the other number. So here's how I deal with how to, I guess, expand out this last piece. So this P1 is a prime number. I can think about all of the rest of this stuff as n. And so I'm now going to be able to start rewriting this. So each time I look at a prime number and the rest, I'm going to get a factor of p minus 1. So we basically can now rewrite this in the following way. So each of these prime numbers that are left over is now going to get a p1 minus 1, a p2 minus 2, minus 1, sorry. And this keeps going until we are left over with only phi of pm, but that's a prime number, and we know that the Euler phi of that is pm minus 1. All right, so now all that's really left for us to do is maybe do a little bit of algebraic work here to get what we want. So this formula is saying I should be able to recapture n, and I get all of these like weird looking factors. So how do I recapture n? This is pretty close to n, but I need to have one more copy of p1, one more copy of p2, all the way up to one more copy of pm. So we still need one more copy of each prime number. How are we going to do that? We're going to notice that, okay, if I look at this first factor over here, I could factor out a p1. And if I do that, what do I get? Well, I'm going to get p1, 1 minus 1 over p1. So all we're doing in each one of these factors that's left over is just factoring out that extra factor that we need to recapture n, and then collecting everything in a way that makes things look nice. So we're going to end up getting something that looks like this. So let's go ahead and recapture all of those missing factors that we need. By factoring out, we get 1 minus 1 over p1. 1 minus 1 over p2, etc. 1 minus 1 over pm. And then we notice that this here is really just n. And there you go. So that's how we prove that one. So we do need those two lemmas. Those lemmas allow us to effectively break up these larger numbers into smaller pieces that we can work with, and then we do a little bit of rearranging to get the generalized formula. So there's our generalized formula. So what does this say? This says if I want to find the Euler Phi number for any positive integer, I really just need to know what its prime power factorization looks like. So let's take a really large number. It's not really that big, but big enough that I would need to think about how to work with a number like this, right? So if I want to find the Euler Phi function for 702, well, the first thing I probably want to do is try to figure out what the prime power factorization for 702 is. So let's see, 702, it's definitely divisible by 3. It's divisible by 3, it's divisible by 2, so it's divisible by 6. So what if I do 702 divided by 6? I get 117. Is 117 prime? No, 117 is divisible by 3 still. Because 7 plus 1 plus 2 is 9. So I know this is at least divisible by... It's actually divisible by 9, isn't it? It's 13 and 9. Okay, so 13 and 9, I said. 13 is prime, and then 9 can be broken up into 3 and 3. So I'm just doing the factor tree approach. You can do whatever approach you want to find the prime power numbers that we're going to need to recapture 702. But the idea here is we're going to be thinking about this now as, instead of 702, I might write this as 2 times 3 cubed times 13. So let's look at the prime power decomposition of 702. I think I captured everything. 1, 2, 3, 4, 5, 3, 4, 5. And so we get 702 times 1 minus 1/2 times 1 minus 1/3 times 1 minus 1/13. And then from here, let's see, we can probably reasonably deal with these fractions, like 1 minus 1/2 is 1/2, 1 minus 1/3 is 2/3, and then 1 minus 1/13 is 12 over 13. So this just gives us maybe an easier way to input some stuff into our calculator. There is some stuff that's going to cancel here too, so maybe like I can do a little bit of work like this. So now I have a way to move forward here. So let's take 702. I'm going to go ahead and multiply by 4 and then divide by 13. So we should get 216. So I would suggest, find a website that will calculate the Euler Phi function or Euler totient function for you. Do a couple examples. Just make sure you're comfortable with how to break up those pieces by using prime power factorization. That's really all we're looking for, probably when we start to work on some of our algorithms a little bit later.